Alright, so I thought before I go on to parallax or relief mapping or anything that makes the walls stand out even more, I will explain what the basic idea is behind normal mapping first, because I think I didn't get the idea through too well in the previous video. And then I will explain how parallax mapping works. And also what the tangent space transform does. Okay, so I think I'll start with the basic idea behind normal mapping. I mean, it's pretty straightforward, really. Imagine you have a surface which is like this or similar. So like that, we want to draw a triangle which has this base, but looks like the surface is like this. How do we do that? It's not that hard, because all that changes, at least for the light, is how the light reflects. So I will move this down so I can draw it. Like, let's say the light shines directly onto the surface, like this. That's not a straight line. This looks more like a straight line. Anyway, now if you see this height map, basically, you can tell, okay, it would basically reflect off like that. And that's pretty fair, I guess. But if we do not calculate stuff with this height, it would just reflect backwards. Or let's say it shines onto the surface like that. If we do not use the normal map, what would happen is it reflects off like that. Because that angle and that angle are the same. And when we use the normal map, we would want it to reflect off like, don't let me lie, we would have to calculate the normal at this point, and that would be the normal from here. So it would probably reflect off like that, or something similar. So the basic idea is we say, okay, the normal at that point is not just straight upward, but instead it's like, let me draw the normal at some points. Here my normal would be like this, and here my normal would be like that. So if I want to know how strong I perceive the light at that point, I will erase all that and draw it again. I want to figure out, okay, here it is. I want to figure out two things. One is how much of the light even or gets reflected from the surface in general. Like, I will draw again some kind of surface like that, maybe. How much gets reflected in general, which is the ambient light calculation we did the last time. The basic idea is, if my normal at that point is like this, because you can see at that point the normal would be like that, but we're still working on a plane. So let's say my normal at that point is like this. Normal. I will draw normals in light blue. And the light hits the surface directly in this direction. Yeah. Well, I will leave it here. Just keep in mind that this is exactly hitting normal. So now we know, okay, that light is pretty bright. I mean, if we shine directly onto the surface, like imagine it's like this, it will not be that bright. I mean, the basic idea is pretty easy. If we shine like a bit tilted on the surface, it will not be as bright, and if we shine from behind, there will be no brightness at all. Except like the ambient color is always applied, but we wouldn't anything that looks a bit bright out of it. Okay, so if from here it's the same thing. Okay, good. Then how specular lighting works, which you pretty much have to use it for normal mapping because otherwise the effect doesn't go around. So imagine this, I will make it back, is the surface that belongs to that normal. And we look from, let's say, here, and the light comes from, let's say, there. Now we want to know how much of the light is reflected directly into our eye. And what we know is, if we have a surface, there you go, and the light is reflected off the surface, then two angles are the same. And these two angles are which color? Let's say black. This one is alpha and that one is also alpha. So the closer our look vector is to well, let's say the light goes in that direction. So here it will go in that direction. And our view vector is like this. Then that's pretty good, right? The light is directly reflected into our eye. But if our view vector is like that, it's not quite as good. So how do we figure out how well the light reflects into our eye? Well, what we do is we figure out the vector which is between the two. And we do that by adding them and then renormalizing the vector. I will move everything a bit to the side. Okay, so let's say this is our view vector and that is our light vector. Now how do we figure out which is the vector in between? Also, just assume they are the same length. I mean, they are not quite the same length here, but generally you have to normalize them, or at least make sure they are the same length before doing this. What you do is you add them together. So how do I make the background transparent? Oh, there you go. Okay. So I will put that vector and then I will renormalize it. So this would be the vector I get when I add the two of them. And if I renormalize it, it should be cut like here. So you can think of an arc between these two, and that the point where the arc cuts the vector will be that. So you can see it's in the middle. Okay, so if we do the same thing here, we will end up with a vector that's like this. And now if we multiply the normal of the surface with the half view vector, which is the vector which is halfway between the light and the view vector, we get the light that is reflected directly into our eye. By doing that, we know, okay, I have to make that pixel much brighter than all the other stuff, because the ambient light is just like the light that's there. Like, think of looking at the wall or something. The light is not directly reflected into your eye, but you can still see it. It's not pitch black. Or let's say, what does everyone have in their room? Think of a knife or a fork when you're too lazy to put it away, or a glass maybe. If you have a glass which is circular, there's definitely one spot where the light is reflected into your eye, and you can see it's much brighter. So also the area is very limited. So what we do is we take the dot product of the normal of the normal and the of the half view vector. Should make this a bit wider and the writing a bit smaller. Dot product of the normal and the half view vector, and then we take it to some power, let's say the power of 2 or the power of 3, and by that, because all the values are between 0 and 1, we limit the area where we have this bright light. And that's the basic idea of normal mapping and how we reflect the light of our surface then. That's all for this video. The next video will be the theory behind parallax mapping, and then we'll do parallax mapping, just because it looks so awesome. Thanks for watching.